Hi, I'm Siva. I'm going to be talking about our work on template inference and the tool SelfStarter for finding misconfigurations. This work was a collaboration between my professors Todd, George, and Yuval at UCLA with Ryan, Beckett, and Karthick from Microsoft. Network misconfigurations are still common today. We see in the news and top-line news articles about some network being down or about some cloud outages. In all of this, users have connectivity issues, and on the other side, for the companies involved, they experience losses. So the key question today is, how can we detect misconfigurations? Researchers in the past decade have traditionally attempted to combat these outages by proposing various formal methods collectively called as network verification. The core theme in these network verification tools is that they build a mathematical model of the network to analyze it logically and take as input the router configs or some form of the network state and the properties or the invariants they want to check on the network through a spec. Given the router configs and spec as the input to the verifier certifies whether the network is bug-free or provides you examples that shows violations of the specification. However, these approaches have an important practical limitation, which is that formal specifications are in general not available. That is, users must provide an explicit formal specification of the network's intended behavior. However, specs tends to be informal, incomplete, and ambiguous as it's harder to express things formally and precisely. So for our purpose, we can assume that such specifications do not exist. In the last talk from config to spec, we have seen an approach of trying to synthesize specs from the configs, but in my talk, I will show you a way of deriving useful insights without requiring a formal spec. So the key question that we address in our work is how to find misconfigurations without an explicit specification. Here, we are inspired by the software paradigm bugs as deviant behavior, which simply put states that if you don't know what the correct behavior is, but you notice that thousands does X and 1 does Y, then it's very likely that X is the intended behavior and that 1 which is doing the Y is probably misconfigured. But how is this paradigm relevant even in networks? This paradigm is a natural fit for network configuration since by design, many nodes configurations are intended to be highly similar to one another through designation of roles to devices. We exploit these network device roles to apply the above paradigm. But what are these roles? Routers in a network are generally assigned certain roles based on their use. For example, a network can assign certain routers as border routers, which might be performing eBGP with the ISP and might be rich in route policies. Similarly, the internal routers might be called as core routers or distribution routers and might be rich in access control lists. And routers in the same role of a network are typically configured similarly. Given this observation, first we have to define when are two router configs considered to be similar, that is, they are doing the same thing, and how to define and identify deviations. A naive approach would be to use exact configuration equivalence. Two router configs are treated as similar and grouped together if they are configured exactly the same. A group with few configs is likely misconfigured. Such an approach can identify outliers in the simpler aspects of configuration, such as the set of DNS servers or the MTU values on interfaces. However, this is too strong an assumption for more complex aspects like access control lists and route policies. That is, if we group the access control list configs using exact configuration equivalence, we might very likely end up with each router in its own group, and it's not useful for outlier detection. This is because even though the ACLs have a lot of structural similarity, they have slight variations from router to account for intentional differences, let's say for local IPs. Instead, we propose a novel approach of inferring parameterized templates to distinguish intentional differences from likely bugs. Each template is a configuration snippet definition that is optionally parameterized by various pieces of data. Two routers are considered similar and grouped together if they are instantiations of the same template. In other words, we model the likely intentional differences as variations between the nodes in a template, while modeling the likely erroneous differences as variations across template. In short, we make the following contributions. We are the first to propose an automatic template inference algorithm for any configuration segment. A segment is any logical unit of a configuration, such as a BGP session or an access control list or a route policy. We show the concrete instantiations of this generic algorithm for 3 widely used segments, namely the access control list, prefix list, and route policies. We build our tool SelfStarter to find potential bugs in router configurations, which also provides actionable feedback to the operators using the above algorithm. We evaluated SelfStarter on 3 real-life large-scale networks, namely Microsoft Data Center, Microsoft Wide Area Network, and a large campus network, and found 43 previously unknown bugs. Before we go into the details, I will give an overview of the end-to-end design of the SelfStarter. Router configs are the main input to the SelfStarter. Here, we also require the information about the role of each router. We would be able to get this information from the router names itself, or we can take the help of the network engineer. It is to be noted that this is a very minimal amount of information that we require from the network engineer, and in general, the network engineers are very well aware of the router roles in their network. Given this information, SelfStarter first separates the configs for each role. Then, for each role, for each commonly found segment, SelfStarter combines them to generate the templates. For example, if the routers in R1 define an ACLX, then SelfStarter combines the definition of ACLX from all the R1 routers and say has produced 3 templates, T1, T2, and T3. Similarly, for another ACL named Y, SelfStarter might produce only 1 template, and so on and so forth for other ACLs, prefix lists, and route policies. This is so far the template inference stage. Templates by themselves have many uses. For example, to understand the current configuration policy or to understand the configuration changes between 2 snapshots. One very specific and useful way that I'm going to describe in this talk is for outlier detection. In case, let's consider that we found that the number of instantiations of template T1 are greater than T2 and similarly for T3. Then it is very likely that T2 and T3 routers that are instantiations are likely misconfigured. Let's look at a concrete example from the campus network. This is a real example from the dataset where we found that the campus network has 1,000 routers. And let's look at one specific role. Let's say the role is the building routers of each department. And there are 106 router configs. And in all of these 106 configs, we found that there are many commonly defined ACLs. And let's say the common ACLs are like auxiliary in and auxiliary out. Let's look at the auxiliary in. For the auxiliary in ACL, SelfStarter inferred that from the 106 configs, it inferred 3 templates. And their group sizes are 88, 16, and 2. So which means that there are 88 routers which have the ACL X, which are instantiations of the template T1. There are 16 routers which have the definition of ACL X, which are instantiations of the template T2. Similarly, the 2. And although by this point, we know that these 18 routers are outliers based on the template clustering and their sizes, but it will be more useful to know why these are outliers and what relevant changes have to be made to the configuration in order to fix it. Having this information would reduce the burden on network operators and streamline the process of fixing bugs. Let's zoom in these templates and see how SelfStarter provides actionable feedback to the operators. As said earlier, the input is 106 ACL configurations from the BR role in the campus network. For network operators, to easily compare templates, we combine all the 3 inferred templates into a meta template. A meta template is a concise representation of the 3 inferred templates, highlighting their commonalities and differences. A meta template is a sequence of parameterized configuration lines. Capital letters like A and B are parameters representing values that differ across ACLs that contain the corresponding line. The meta template is complete. Every line that appears in some ACL is represented by a line in the meta template. Legend on the right side identifies the 3 templates that SelfStarter inferred. Each column represents a group of nodes that share a common template. Each row represents a set of lines through a color to allow users to easily see which lines of the meta template belong to each template. Next, we will see how to get the template of each group from the meta template. For example, let's consider the group 1 column, which basically has 2 colored rows, the green and the red. So if you pick all the green and red color lines from the meta template, we get the template of the group 1. Specifically, the group 1 routers are the instantiations of template that consists of line 1, 2, 6, and 7, 8, as in the order described in the meta template. For group 2 consists of all the 3 colored lines, so the template of group 2 consists of all the 8 lines from the meta template. For group 3, it consists of only the green and yellow lines, so the red line is missing from the template of group 3. So far, we have seen the templates. Now we'll describe an approach to see how we can identify deviations from this. As said earlier, the number of ACLs in group 2 and group 3 are significantly lower when compared to the ACLs in group 1, so they are very likely misconfigured. As I said earlier, it is important to know that there are outliers, but it is more important to know how they are different from the majority. And the meta template does the job for us. Meta template provides an actionable feedback showing concisely how group 1 differs from group 2. SelfStarter also allows us to find deviances not only at the coarse granularity of the groups, but at finer granularity of a line. For example, consider the parameter A and its value for the ACLs in group 1. We found that the value of parameter A is 255 in 78 out of the 88 ACLs, and it is 127 in 10 of the ACLs. Similarly, as we saw for the groups, it's the case that these 127 are very likely misconfigured. SelfStarter can only detect outliers, so we need to confirm with the operators whether these are actually misconfigurations or not. Given this meta template and the outliers, the network operator was able to easily quickly say that these are actually misconfigured. Here, I would like to highlight that SelfStarter started without any prior knowledge of what the correct behavior or policy is and identified these policy violations based on template inference. So far, we have seen what the tool outputs and how it is useful. Next, I will explain the key ideas in inferring the templates. To explain the key challenges and our algorithm, I will use ACLs as example, but this is a generic algorithm and is applicable to other segments like route policies and prefix list. Consider the 2 ACLs and assume that we are trying to infer their template. Their first lines are identical, so clearly they should be matched to one another. However, their second lines differ. They apply to different source IP addresses. A naive approach, as said earlier, is simply not to match these lines together. However, such an exact matching criteria is too strong, as it is common for corresponding ACLs to be similar but not exactly equal. Therefore, the algorithm must be able to match non-identical lines to one another. We meet this requirement using parameterization. In this example, we can introduce a parameter to represent the third octet in the source IP address, indicating that this octet differs in each ACL while the rest of the line is identical. Similar is the case for the line 3. But too much parameterization can also hurt by masking important differences. For example, consider line 4 in both the ACLs. We notice that they differ in 4 octets, and this might be too much parameterization. But to say that this is too much parameterization, do we have a better parameterized line? Yes. If you look at line 4 and line 5, you notice that there is only 1 octet difference. Similarly, line 5 here and line 4 have only 1 octet difference. This crisscross matching introduces less parameters and produces better readable template. This reordering, should we allow this reordering or not? This reordering is innocuous and is safe to allow as they are a contiguous sequence of permit lines. So the key challenge is how to allow certain reorderings for a better template, but not arbitrary reorderings. In general, reordering lines in an ACLs can be dangerous as it might change the behavior. Specifically, reordering a permit line and a deny line can in general change the semantics of an ACL. However, some reorderings are innocuous and should not be flagged as deviations as this one. We resolve this challenge by representing an ACL not as a sequence of lines, but as a sequence of blocks, where a block is a sequence of lines that can be arbitrarily reordered. A block is a general term and can be defined as the operator wants. I will show you how we define block for ACLs in the next slide. For ACLs, a block is a contiguous sequence of either permit or deny lines. For example, in ACL1, there are 4 blocks, And the first 3 blocks contains 1 line each. The last block consists of 2 lines. After we generate the blocks, now you have a block sequence 1 from ACL1 and block sequence 2 from ACL2. Now we want to match these block sequences and combine them together and get the final template. To align the blocks, we use sequence alignment to prevent cross-block reorderings. And to match lines to allow reorderings, we use minimum weight bipartite matching to allow within block reorderings. Due to the interplay between these 2 matchings, we can allow certain reorderings and prefer some matchings over the other. I will not go into the details. Please see your paper for more details. So using this novel 2-level approach, we match configs with one another and generate the template. The final template for these 2 configs looks like this, where we allow the reordering and abstract the concrete values where they differ by using parameters. Next, I will describe the results of running SelfStarter on 3 networks. First, I will introduce a key term triple. A triple is a tuple of segment type, role, and segment name. Segment type is basically like ACL prefix list or route policy, and a role is the role of the routers, and segment name is the name of the ACL or prefix list. For each triple, SelfStarter generates a meta template. To evaluate SelfStarter, we applied it to a collection of data center networks from Microsoft Wide Area Network, and the campus network of a large university. These networks differ widely in their structure, scale, and management style. Consistent triple is a set of triples where the meta template has only one template in it. Inconsistent triple is a meta template in which the meta template consists of at least 2 templates. Of the identified ones, we could only investigate some of them, and of the investigated ones, we show the true positives. SelfStarter had 100% true positive rate in almost all of them except for the wide area prefix list. The reason for the wide area prefix list having low true positive rate is because these prefix lists dynamically expand to multiple lines. Most of these prefix lists are dynamically created by expanding an existing set of addresses defined elsewhere in the configuration, such as a set of local IPs or NTP servers. In our template inference algorithm, we generalize aspects of a line through parameters, and all the device configs that are instantiations of a template have the same number of lines. As these prefix lists in wide area network have different number of lines, even among the devices in a single role, there are way too many groups generated from SelfStarter. As a result, we found very low true positive rate. Next, I will explain the source of misconfigurations for the Microsoft networks, and I will leave the campus network due to lack of time. Microsoft Wide Area Network is managed by the operators with the help of some Perl scripts. Some of these scripts have certain templates embedded in them. These templates are not as sophisticated as the ones SelfStarter inferred. Sometimes these templates are more like a bag of commands. The reason for the errors in Microsoft Wide Area Network is specifically because of these scripts. Specifically, a script that checks for the existence of certain commands in a route policy accidentally did not consider the order of these commands. Since SelfStarter takes order into account, its meta template contained multiple groups and hence identified ordering errors that change the behavior and that the script missed. Another class of errors was due to a spurious community tag being added to some route policies by the operators. Microsoft data centers are a fully automated service where they have handwritten templates, and the software service constantly checks whether the router config deviates from the template and periodically updates it. The reason that we found misconfigurations, these inconsistencies were already known because there is a software service running through it. And the reason for these inconsistencies is delayed updates, because the software service has to take into certain constraints as to when a router can be refreshed, because sometimes the routers are the top of the rack routers and cannot be refreshed immediately. To conclude, we present a generic template inference algorithm for configuration segments and our tool SelfStarter for finding potential network bugs. And it also provides actionable feedback through meta templates. And we found 43 previously unknown bugs in Microsoft networks and campus network. And the source code is publicly available. And thank you, and happy to take questions.
Questions?
Hi. Just wondering if cases where the configuration itself is not line by line, like for example, if you were to look at an interface configuration, which is typically like a collection of lines,
yes.
Would you be able to extend this approach to
yes.
that?
So this work was done in earlier, like 10 years ago by Minerals paper, where they use property equivalence for interfaces.
Okay.
So for interfaces, you can assume that there is a bag of commands, and you can define them as a single block and use this algorithm. Or you can use a property-based equivalence saying that the interfaces have to have some HSRB defined or some protocol defined in them.
Okay, thank you.
So you talked about that there can be many uses for these templates. Sort of in discussing with network engineers, were there implicit templates that they weren't thinking about using, but in reality exist and could make their management easier?
Sorry, I did not.
So they presumably in the scripts they had some known templates they were using, right?
Yeah.
Were there templates you discovered that they didn't think about as templates, but they were like, oh, this is actually a useful template that could make our management easier, and we could do some automation here?
Yes, both in wider network and campus network we found this. Like they said, oh, these templates are useful for us too.
Okay.
Let's thank the speaker.